The latest Yellowstone Supervolcano Caldera Chronicles just came out. This has to do with the deformation of the supervolcano's caldera, the InSAR magic deformation camera, and what it reveals. This is USGS, Yellowstone Volcano Observatory. InSAR, this is dated today, May 6th. InSAR, the magic deformation camera that no one saw coming. As we know, the Yellowstone Caldera Chronicles is a weekly column written by the scientists and the collaborators of Yellowstone Volcano Observatory. This contribution is from Dan Zurizen, geologist at the U.S. Geological Survey. Toting their surveying instruments to the tops of mountains or across continents, ancient 20th century geodesists might have dreamed of an easy way to measure precise locations and track changes in ground motion. That's the deformation over time. Today, that dream has been realized with the GPS and the InSAR. Neither was a result of fanciful dreams or foresight. Two of today's most effective techniques for studying ground deformation were fortuitous afterthoughts. The GPS story was covered in earlier Caldera Chronicle articles. The InSAR story requires a brief introduction. Radars come in two basic types: tracking radars and imaging radars. Tracking radars ping a certain target, record the reflective signal, and measure 1. How long it took for the ping's round trip, and 2. The frequency of the return signal. The travel time is a measure of distance to the target. The target's velocity can be determined from the frequency of the return signal, which differs from that of the transmitted signal as a result of the Doppler effect. This is the effect that makes a siren sound different when it's coming towards you versus moving away from you, for example. Air traffic control radars and police speed detectors work on this principle. Now, imaging radars reveal much more about their targets and how far and how fast. They illuminate the target and record the pattern of reflective energy as an image, akin to a photograph, but different in some important respects. The pattern depends on properties, size, shape, orientation, etc., of many individual reflectors that contribute to each pixel in the image. Radar images look different than conventional photographs, and they reveal different things about the target. There are two types of imaging radars: the real aperture radars and synthetic aperture radars, SARs, for example. The resolution of an imaging radar depends on several factors, including the antenna size, that is, bigger is better. To achieve useful surface resolution with orbiting real aperture radar would require an enormous antenna, much too large to be practical. But radar engineers are a clever bunch, able to conjure up, synthesize is the technical term, enormous virtual antennas by taking advantage of the orbital motion of a real aperture radar and the Doppler effect mentioned earlier. The details aren't important here. The point is rather that SARs with sufficient resolution to see your car from orbit are a reality. Recognizing that SAR satellite could provide unique and valuable information about surface features and characteristics, the European Space Agency ESA launched the ERS-1 satellite in 1991 with a mission to acquire radar images of the entire globe. And what we have here today given to us by Yellowstone Volcano Observatory is the color bands in the radar interferogram that depict the patterns of surface deformation at the Yellowstone caldera from September 22, 2004 to August 23, 2006. So it's basically a 2-year period. The southwest and northeast parts of the caldera floor rose 4.3 inches in 2 years and 5.9 inches respectively, while the North Caldera rim near Norris Geyser Basin subsided about 2.8 inches. And this is in a 2-year period. Scientists at the Jet Propulsion Laboratory realized that under certain circumstances. SAR images could be combined to produce derivative images called interferograms. SAR images show how the surface would look to a pair of radar-sensitive eyes. An interferogram shows how much the surface moved during the time interval between SAR images with millimeter scale precision. 1 millimeter is less than 1/6 of an inch, for example. With InSAR, the interferometric synthetic aperture radar, scientists can create snapshots of surface deformation without ever trudging to a mountaintop or across a continent. A new branch of geodesy was born that way. A remarkable demonstration of InSAR's capability came in 1993, when several French scientists produced an interferogram from ERS-1 images showing in glorious detail the patterns of surface disruption caused by the 1992 magnitude 7.3 Landers, California earthquake. In the decades prior, geologists had measured fault scraps, geodesists had surveyed nearby benchmarks, and modelers had calculated how the Earth might move during a major earthquake. And for the first time ever, all could marvel at a picture, quote-unquote, of what actually happened. It was a snapshot taken from space by a satellite designed to do something else. Today, scientists are using InSAR, the magic deformation camera, to study deformation at Yellowstone and elsewhere around the globe. Using the technique, it has been possible to get an overall picture of Yellowstone deformation, revealing some interesting patterns of ground motion, and we'll discuss some of these patterns in future issues of Yellowstone Caldera Chronicles. Now, the deformation in monitoring in Yellowstone National Park, as we know, continues recording temporary deployments using GPS systems, receivers and benchmarks on solid monuments employed at Yellowstone to precisely record their position. The time variations over days, months, years provide the velocity in centimeters per year. Now, a lot of people say, why not use inches, why use centimeters, why use a metric system? It's because you can use the math much more easily using a metric system, which has to do with tens and hundreds and thousands. It's very workable with math. That's why they use a metric system in science. So time variations over days, months, years of the site relative to the rest of the points in Yellowstone and to the rest of North America. The velocity fields map spatial variations of the ground due to volcanic processes, that is the magma and the hydrothermal and even the gas emissions that cause the ground to subside or to rise. The changes of magma, water, and gas. Measurements of ground motion using GPS at Yellowstone provide a method of monitoring the activity, its active volcano-tectonic processes that are necessary for understanding the properties and locations of the sources, as well as providing information on the possible premonitory motions that precede a volcanic eruption or an earthquake event. So the GPS stations are maintained by the Plate Boundary Observatory via UNAVCO, and the data are transmitted via radio and satellite links to various groups around the world for recording and processing. The GPS deformation data, the stations and time series data for Yellowstone region from the University of Utah, Yellowstone Snake River Plain, Wasatch GPS horizontal velocities data, Yellowstone Caldera GPS derived velocity maps, station history, characteristics and status, benchmark, but I'm going to go to the first one, GPS stations and time series data for the Yellowstone. And they have them all over. It shows you there, if you click on the proper Yellowstone, I'll leave a link below for you, for the Yellowstone Volcano Observatory under monitoring and under deformation. Go to the end of the page, and GPS deformation data is at the bottom of the page. Click the first thing, GPS stations and time series data, and you see where the GPS stations are. Let's go, first of all, it's over Yellowstone, it's over at Montana. It's at the corner of upper northeast. Well, let's go to the lake. We're going to P709, and it shows you, this is the UNAFCO graphs, and it shows you from 2006 to 2014. I don't know if for some reason they don't have any information for 2010, maybe they were down. It shows you that it's, let's see, the station 709, and you're looking at the fact that the north, if it goes up, it's north, if it goes down, it's south. And at 2000, it went up, this is in millimeters. So it went, we're talking about a slight change north, it's going up north. And this east would be up, west would be down. So it's going down west. And this is vertical or horizontal, it's just about the same. And I'll show you where we got it from. There's a whole bunch of stations that you can see. This here is Yellowstone Lake, and we just happened to pick that one there. This is Montana. This is the area that we had. Oh, this here, as you can see, those red circles, those are the hot spots that they progressed. This must be towards Idaho here. This is the progression of the hot spots from millions of years ago. This is the latest caldera area. This is the lake. The magma chamber is right under the lake of Yellowstone Lake, and this is the latest eruption being 2.1 million years ago, and this was like 4 million years ago, 6 million years ago, 7, 8, 10 to 12 million years ago in Idaho. That's a supervolcano, by the way, there. And there's a lot of and that extends all the way down. If you extend it all the way down, southeast, it goes all the way down to where we have Long Valley Caldera, which is another supervolcano in California. It goes all the way through Nevada, all the way through Idaho, and as the hotspot progresses, it's now found under the magma plume is right under Yellowstone Lake. So we saw that one. Let's go back to that one again. Here, that's the one that we saw. Let's take another one. Let's take one that's around the area that, this only goes up to 2016 though, for some odd reason. This is where we had the quake swarm, basically. This is Idaho, this is Montana. The Montana quake swarm. This is Norris, this is the Norris Geyser Basin. And we see that it's basically, it was north and it went south, and it's going back up north again for the year, for 14 years, from 2000 to 2014. And east is going down west, and it's vertical, basically it's going up. It's rising as of 2014. Okay, so you can see for yourself all these. Let's go here, down here to Idaho. Let's go down to that one that used to be. Ooh, that's got a lot of activity. Oh, that has a lot of activity, right? This is going south. For 8 years time period, going south. And it's going west. It's going southwest. And a little bit of deformation up. It's rising a little bit in 8 years. And this is millimeters, like 100 millimeters. What is that? It must be like 10 millimeters. It went up 10 millimeters. So this, you can see that's really a big amount. So you can see for yourself what's happening in the area. Deformation. Should we take this one here, which is, oh, let's take that one there. Okay. P459. Again, it's going south, and you have amazing cyclical event. Look at this. This is really cyclical. East and it's going east and then go down west. It goes east and then west, and east and west, and then east and west, east west, east west. Just about every year. That's really rocking. And vertical, up and down and up and down and up and down, the same thing. That's really rocking. That was at 4:59. This one here, that's really rocking. So you can see for yourself. There's a lot of activity in Yellowstone. Okay, that was the University of Utah, UNAFCO. Let's go here. April 2005 to March 2012. Seismology and active tectonics research. Due to the obvious separation in distance since the 1990s, the Yellowstone and Wasatch Front GPS networks have been viewed as two individual networks. Over the past several years, the number of GPS stations in both Yellowstone and Wasatch Front have been increasing in number and in overall area covered. As seen by the figure here, the two networks are beginning to merge into one much larger network, and this addition to our web page shows experimental velocity fields result combination of Yellowstone and Wasatch. Now, look, it's moving at 3 millimeters a year. Amazing. It's Colorado, Utah, Nevada, Idaho, Wyoming. It shows you how things are moving. Amazing. This is a lot of movement here. Very huge movement here. This is the lake that we saw that had the cyclical movement up and down, remember? Less movement up here. It's amazing. So there's a lot of stretching and activity. The earth is always moving. So, should we see the, I want to see the temperature. What is the temperature for, let's go here, thermal remote sensing. Taking the, okay, that's the temperature from space. No, we don't want it from space. Okay. I wanted to see the stream flow data. Let's go here. The stream flow data. Amazing. And gas. This is pretty old. This is going all the way back to 2011. Seismic swarm. Because of the gas and hydrology. Okay. Temperature measurements for the North Geyser Basin. Or Steamboat Geyser, let's see. I don't know if we have any for Steamboat Geyser. Here it stopped in 2014 for some reason. And hold on, let's see the pools. Steamboat Geyser. Let's see if it's got anything going up. No. Okay, that's because they don't have any temperature monitors there. They haven't had them since Steamboat was erupting last year, and they're still not up for some. That's, to me, very sad, because it's the biggest geyser in the world. They can go up to 600 feet height, and they still don't have their monitors up. That's really sad. They do have thermal monitors, temperature monitors in other areas. They should bring one over here. So I'll leave links below for you for this wonderful site to look through. And this is on Yellowstone Volcano Observatory, the Chronicles. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.